Hi everyone, welcome to the class. I am Diksha Kaushal, your chemistry master teacher. And students, today we are going to talk about, in the last class we discussed Thomson model, Rutherford model and somewhat about EM waves as well. And today we are going to talk about photoelectric effect, black body radiation and Planck's theory. So, what exactly happened? Okay. So, before that, let me just see that how many of you have actually done the homework. So, the students who have done the homework are Abhijit, and then very good. Okay, correct answer is not available. Okay, C and this Yashu is also done the homework. So, very good. These four students have done the homework, and I would advise all the students out there, right? If you actually, want to be disciplined and consistent, then guys, you have to do the homework, right? Otherwise, nothing is going to work, right? And guys, in the description box you will see some basic concepts of chemistry, DPP, and let me know how many of you have actually solved it. I asked you to solve it, but I don't know how many of you have actually done it or not. If you have solved it, you can give on the Telegram channel. What is our Telegram channel? This is Vedantu JEE English Telegram channel, right? Over here, you can scan this and get into the Telegram channel. Then there is an option of leave a comment, right? On that, you can also upload a photo. So I would love to see that you have actually solved the DPPs, right? Because it takes hard work to prepare the DPPs for you. And when I see that you guys are actually solving it, it will motivate me further. So after this class, I'll ask you DPP's solutions here. So let's see how many of you are lying that you have done the DPP, how many of you are not lying that you have done the DPP. Okay. And students, in today's class, just like in the last class, we discussed with the help of simulation of Rutherford model. We are going to discuss this class with the simulation of black body radiation and with photoelectric effect, right? Okay. So everybody, everyone in the chat box, let's start. See, in the last class, we discussed about electromagnetic waves. I told you that here electric magnetic field will be perpendicular and these two will be perpendicular to the propagation of the wave. If wave is going in this direction, this is the electric field, this will be the magnetic field. So, electric and magnetic field is perpendicular to the propagation of the wave and they are also perpendicular to each other. That is electromagnetic wave, and its characteristics also we discussed about lambda, then what is frequency, wave, what is wave number, all of these things we already discussed about. Now, next is we also discussed about the spectrum, that how the spectrum is. If you talk about the increasing wavelength, you should remember this particular spectrum here, this particular order here, that is gamma, X, UV visible, infra, micro, radio. Okay, gamma's X, UV is visible, right? Gamma's X, UV is visible. Information has leaked to which place? Information, micro, radio. Information is there on microwaves and radio, right? So gamma gamma X UV visible, information, micro, radio. Okay, that's how you're going to learn this particular spectrum. Now, students, see one thing. First thing, why we are studying black body radiations. Okay, so what was questioned here, that electromagnetic radiations are waves, right? That's why we are calling it electromagnetic waves. Okay, that's why we are calling it electromagnetic waves. Then there were some, we know that if I say electromagnetic radiations are waves, right? Then we have so many things that are in favor of that. Like you have Young's modulus experiment, you have done interference in physics, right? Then you have done diffraction in physics, right? This chapter is quite related to physics, right? So then you have done dispersion, right? What are the other phenomena you have done? You have done reflection, right? You have done refraction. So all these phenomena are in favor. They are saying yes, electromagnetic radiations are waves. You have discussed all of these in physics. You have not discussed till yet. You will discuss it. Don't worry about that, right? So these five phenomena are telling us that electromagnetic radiations are waves, right? But there are some experiments that are questioning this part, that they can be particle also, right? So this is where the duality of wave and particle nature will be questioned, right? In the end, we will also talk about dual nature, but for that we have to understand what are these experiments that are telling that it is having a particle nature. Okay, yes. So now let's discuss about the first experiment that is telling that this electromagnetic radiation is particle nature, is black body radiation. Okay, black body radiation. Now, trust me, this concept very few students are able to understand because the clarity is not there. So, I'll give you one clarity on this. See, you have to imagine everything, what is happening in your life. Okay? Yes, everyone? So, till now, what we are discussing? We are discussing electromagnetic radiations, right? In that, we are going to talk about black body radiation. That why black body radiation? First, you have to understand what is black body radiation. See, you talk about anything, right? Let's talk about which thing? Let's talk about this paper here, right? Let's talk about this paper, right? Now this paper, if you keep it in sun, it will absorb some radiations, right? Why am I able to see that this paper is of green color? Why? Because this is reflecting green color. It is not absorbing green color. It is reflecting green color, right? So that means if I talk about this red color, let's say I talk about this red color, okay? This is red color, right? This is the red color. Now, why am I able to see this red color? Why you can see that this is of red color? Because this is absorbing some radiation from the sun, then it is emitting the wavelength or frequency of red color. That's why we are able to see red color, right? Similarly, same process goes to everything that we see around us. Now see one thing, if you have a, this is the thing that you have, anything, I'm just talking about anything you have, let's say a piece of pen, board, stick, whatever you have. You keep it in under sun, it will absorb the heat. It will absorb the heat, right? Now, when it absorbs the heat, it will have some kinetic energy over here. Some kinetic energy will be there. Some electromagnetic radiations will be there. We are not getting into that. You just have to see the overview of this thing. That whenever you have something, you keep it under sun, right? Even in the environment, it is absorbing some rays, right? But what it is reflecting, we are able to see that. That what it is reflecting, we can see the color of that, right? Now, you must have heard everyone saying that it's so warm outside, let's not wear black. Now, why we tend to not wear black color when it is very hot summer day? What is the reason? You must have heard always it is like, it's black, it will be very warm outside, it will be very difficult to wear black. Why? Because black is a color, right, which will absorb all the radiations and it will not reflect the radiations, right? It's not like black is not reflecting, like it is reflecting, right? That's why we are able to see it. But it's not reflecting any particular, like to that much extent. Like it is reflecting, right? There is no exact black body that we have in reality. So basically a black body is something which only absorbs, it will not emit, it will emit 0%. But in reality, just like we talk about real gases, ideal gases, in reality, we don't have any such black body. We have gray bodies, which can absorb, which will emit to a very small, instant, very small instant. That is our gray body. A black body is thing that will emit 0%. Very rare bodies are that which will emit 0%, right? They will only absorb. Like you have black hole. It will absorb everything that you give it. Even earth, it will take, right? It will not give you anything, right? So same is that black body is, it is going to absorb the radiations, right? Clear on that, what is the black body, right? Now, let's talk about the bulb. Okay, let's talk about the light that you have. So, it will be very interesting. The light that we see, right, the bulb, for example, you have bulb of tungsten, all these things. How come they are giving us light? How come they are giving us glow? That is based on black body radiation, right? So, we'll see what exactly is black body radiation. First thing is black body. And after that, once we know that what is black body, let's talk about this phenomena here. He said that when we heat an iron rod is actually a gray body. It is approximately same to black body. Right? It first turns into red, then white, then blue at a very, very high temperature. What is the reason behind that? Right? So what we saw that if you talk about red here, right? This is red, right? This is red. Can you see that? Wait a minute. Can you see that if you talk about this is the increasing wavelength, red has maximum lambda and this has minimum lambda. Okay, just remember this thing for now, that red has maximum lambda. Now let's talk about this thing, what is going to happen, right? Now, what is happening in black body? That it is absorbing a lot of energies. It is absorbing a lot of energies, right? Now, according to the temperature, it will start reflecting which color to give, right? So, for example, I talk about a filament of the bulb. You have a bulb, right? So, bulb is heating up, heating up, heating up, heating up, right? That's why you can't touch the bulb because it is very heated up, right? So now we have shifted to LEDs, but if you talk about tungsten bulb, right, we used to heat it up, right, with the electricity. And after that, because of that heated up thing, right, the heat waves are coming out of it, right. Now, what you will see is that out of these 100% heat waves that are coming out of the bulb, maybe 5% is what is giving you glow, that is producing light, because these 5% are in the visible range. Rest of the 95% are in some other range that we are not able to see. Maybe in infrared range, right, that we are not able to see ourselves, right? So in our body also, right, our body is absorbing and emitting radiations also. It is also emitting heat, right? That's why your hands will not be very cold. It will be warm, right? If you're not sitting in AC, of course, right? So why it is warm? Because it is producing, it is emitting heat here, right? How come it is emitting heat? Because whenever a body absorbs the radiation, it will have kinetic energy over here, which will produce its own electric and magnetic field, and that's how it is going to start emitting the heat as well. Now, if you're not able to understand this, just remember one thing, not that much detail is not in your syllabus. Just remember that something is absorbing. If it is absorbing, if it is emitting to 100%, yes, if it is black body radiation is the one that is not going to emit anything, right? But in reality, we don't have as such black body, we have gray body, so we take it as black body only. So in our universe, what happens? Everything is emitting some light or heat waves, anything they are emitting, right? So now, more the temperature, different will be how much lambda, how much wavelength they are going to emit. Because emission will be in the form of radiations, right? So that's why what I was telling you about the filament of the bulb, what you will see, if this is the bulb, it is glowing, right? It is glowing here. So what you will see, I know my drawing skills are really bad, guys, right? So if it is glowing, it is, we can see that glow, that yellow light or whatever light you can see it is giving you that light. And I'm not talking about LED bulbs. I'm talking about old tungsten bulbs I'm talking about, right? So these lights actually only 5% or even less we were able to see was glowing, right? In the visible region. More you will see is heat, right? That's why these bulbs tend to make our room heated up. Not that to that extent, but yes, to some extent. So that means the radiation, it's not like what we are saying, it's also what we are not able to see. Like from our body, it is emitting heat, but are you able to see something out of my body? No, right? Because it is emitting heat in the infrared region that you are not able to see, right? So that is the thing that you should remember with the emittance, right? Now, I'll talk about what exactly is happening here. So for that, let's talk about this thing, why the color change is there with the temperature. Let's talk about that, right? So if you see this here, guys, if you see this here, this is the black body radiation graph. Let's say this is a lower temperature of the earth, right? Now I increase it to a light bulb. Can you see maximum? Can you see this lambda? See, this is the wavelength. This is the density, like maximum light what you can observe. Here maximum light, maximum is this point, is the maximum. Can you see? This is a graph like this, guys. This is a graph now like this. Like this is the graph. Let me just draw the graph for you. It's a graph like this. Okay? It's a graph like this. This is the graph that you will see. This is the graph that you will see. And you have to focus that this is the maximum. Maximum intensity is at this lambda. Maximum intensity is at this lambda. That means maximum radiations that it is giving is in this particular region, right? So now you will see that, wait a minute. Now you will see that how it is affecting the graph. Okay, so if I have a light bulb, can you see that maximum radiations are over here, not in the visible region, right? That's why I told you that very minimum light bulb, the radiations that it is giving, very minimum radiations we are able to see, because only this part is there in the visible range. Rest of the part is there in the infrared range, different ranges that we are not able to see, right? Okay, now as I extend this, can you see it is falling in now more in the visible range, as I go beyond, as I go to sun's temperature, which is very high, 49, around 6000 Kelvin. Can you see if you have sun temperature, right? Then what are the maximum range? This much is there in the visible range. That means maximum intensity is there in the visible range. Very rare is there in the infrared or other ranges. If you again keep it down, if you have something in middle, like you have 4500, which is also a very high temperature, this is at this particular range. So this is the variation of the graph that we are talking about, right? That as the temperature is increasing, the maximum intensity, what is changing as the temperature? You just have to know this one thing, right? That as the temperature is changing, can you see temperature is increasing, lambda max is diverting here, right? Lambda, this is the maximum, it is diverting to this side, right? As the temperature is changing, lambda max is changing here, right? So lambda max changing means it is moving to minimum side, right? This is a higher wavelength, this is a lower wavelength. So can I say that as temperature is increasing, lambda max is decreasing? Here this was the lambda max, here this was the lambda max, here this was the lambda max, here this is the here this is the lambda max, here this is the lambda max beyond something here. So I can see that temperature and lambda max has an inverse relation, and this is all that you have to know for black body radiation. In your syllabus, you just have to know this thing, Rest part I just told you so that you're able to understand. Now, if you talk about the iron rod, right? They talked about example of iron rod. So they said that this example is also very important for you. That earlier the temperature was low. Okay. So at a low temperature, firstly it was turning red, right? Firstly it was turning red. Then at more temperature it is turning yellow, a mixture, then white. White will be when all the wavelengths will be equal. Then it is turning to blue. Max will be in a blue phase, right? So that means, can I say that as you increase the temperature to next level, right? You're increasing, the lambda that it is emitting to the maximum, uh, like to the maximum extent, that is changing. That's why the iron rod is changing, right? Okay, that's why the iron rod is firstly red, then it is in the end it will be blue. Because as you increase the temperature, lambda will change, right? Don't apply this on your daily life. Daily life as in you can't say that, ma'am, I have an apple, why it is not changing? Because you're not increasing the temperature to that extent, right? You're not increasing the temperature to that extent. You have to really, really increase the temperature. Can you see what amount of temperature you need? Right? So we can't even, like, in our atmosphere, the temperature is very low, right? As compared to these temperatures, very, very low. So that's why we don't see this often. That's why we have taken an example of iron rod. That's how it is changing, right? Okay. Yes, everybody. So that was about black body radiation. Now I'll just show you that what we'll do here is this graph, okay? This graph. That this is temperature T1, this is temperature T2. First kind of question that they can ask you is, I'll tell you now what kind of question, okay? See, I know you are very curious minds you guys have, right? But we don't have to do PhD in black body radiation, right? Understand one thing, we have to crack J. That's all what we need, right? So that's why I would not advise you to get into that much detail, right? But yes, applications, I told you that this is what happens in our daily life as well. We all are emitting radiations in the IR region because our temperature is not very high, right? If we are burning, then we will emit radiation in a different form, right? In a different color, right? So that's why we are taking example of iron rod. And if you talk about why apple is red, why this is green, right? Because the amount of absorption and emission also depends upon the particles, right? So that is a different, whole together a different topic, right? Okay. Chal. Now let's see black body radiation. First thing is, they can ask you first kind of question. This is T1, this is T2. They will ask you which is greater, T1 or T2. Okay, how do you define it? Let's say it is not written here, then how do I define that which is greater? For that, you have to understand Wien's law. That is, temperature is inversely proportional to maximum lambda. So as temperature is increasing, lambda max will decrease. If I say this is a lambda max here, this is a lambda max here, so can I say lambda max of 2 is less than lambda max of 1? So temperature will be opposite. T of 2 will be greater than T of 1. That's how you write it. Okay. This is a very, very important relation, and based on this, they can ask you easily questions, right? And this is what they ask, right? Okay. Now, same thing that I told you. If lambda max, here they are talking about maximum lambda. If 1 is less than 2, then 3, then temperature is going to have the opposite order. That is according to Wien's law. Okay. Now, let's discuss about Planck's quantum theory. Guys, please focus here, right? So, if you see this is a maximum, right? This is the real graph that we have. This is the real graph that you have. But was it expected? No. Expectation was that the graph should be like this. That the graph should be like this. But in reality, it is moving like this. It is going like this, then decreasing. That was a questionable thing. Why this is happening? Why it is not emitting frequency in a continuous form? Why it is decreasing here, right? So, just to give you an idea, I don't want to jump into the next topic without telling you why it is there. But yes, these things are of really high level. So I'm just giving you a hint of this thing, right? Just a trailer of this thing, right? See, this was the imaginary graph. This was the real graph. So difference was there. Firstly, so you did black body radiation, you know what is the application. Next question was that if you take wave theory here, then it should be like this, right? Then why the graph is like this? It should go continuously. Why there is sudden decrease here, right? So this was proved by Planck. So what is that equation? How he proved it? That is not in our syllabus. Just remember, and this they will not ask you, this, just to let you know that why we are studying in this sequence, okay? So these kind of things they never ask, right? So you need to know this application part, this application part. This I am just telling you to form a like full flow of this lecture. See, real graph is this, imaginary is that. So Planck gave an equation that is not in your syllabus. He gave an equation where he proved that actually these electromagnetic radiation are not waves. He said that they are particles, right? So he said that it's not a ramp. When you go to any place, there will be, especially hospitals, there will be this ramp also, and there will be these stairs also, right? Ramp you can't calculate, it is continuously moving, right? And step is one step, second step, third step, fourth step, fifth step. He said that it is actually in the form of steps. It is actually in the form of packets. Just like you can take 1 dairy milk, 2 dairy milk, you can't say 5 gram of dairy milk, give me 100 gram of dairy milk. You can't say that, right? Because that comes in packets. So he said that this graph will only be proved with my equation that I am giving you, right? So everyone agreed on that. Now we are going to see that equation that he gave to prove that EM radiations are actually particles. They are quantized. Okay, they are quantized. How he said that? He said that energy is emitted or absorbed not continuously but discontinuously in the form of packets. And he simplified that equation, and the simplified version was that energy is given out in the form of E is equals to H mu. That is one quanta. This is one quanta. Okay, so is that each such packet energy is called quantum, and this is one packet. Okay, in one packet you have h mu amount of energy, where this is called Planck's constant, Planck's constant, and this is 6.6 into 10 raised to power minus 34 joule second, and here this is going to be your frequency. Okay, yes everybody, right? This frequency will be dependent, it will be variable, but Planck's constant is going to remain the same. So he gave you that. Now there is a question that might be in your head that, ma'am, is this a wave nature or particle? See, both nature it has. Some things are proving that it is a wave nature, some things are proving it is a particle nature. So that's why we are discussing both. Right? In the end, we will also discuss duality of wave, or duality of electromagnetic radiation. But for that thing, you need to understand that yes, there is particle nature. It is told by Planck's quantum theory that this is having particle nature, and he proved it with one equation. The simplified version is this one, that E is equals to H mu, and you have only this version in your exam. Now, if you remember, in the last class, we also discussed about that C is equals to mu lambda. So can I say mu is equals to C by lambda? So in that case, this will become E is equals to HC by lambda. This is another equation that you will have. This is another equation that you will have. Okay, yes, everybody, clear? I hope so that is clear to everybody here, right? This is another equation, that is E is equals to hc by lambda. Okay, now I'll just give you some formulas which are very, very easy to do this calculation. Wait a minute. Yes. Uh-oh. Sure. Okay. Yes. So sorry about that. Yes. So that is your E is equals to h mu, right? Now, this is the formula that we have already discussed, right? This also we have discussed. Now, see, if you talk about you have n number of quantas, that it will become nh mu. Oh my God, just give me a second. Okay. Yes. Okay, so sorry. Yes. So that is if you have n number of quanta, this will become nh mu. Okay. Yes, everybody. Now we are going to talk about another thing, that is if you tell this in the form of, let's say you are solving this in the form of energy in the form of joules, then you have to convert it in the form of electron volt. For that, you need to know this particular conversion, that 1 EV is equals to 1.6 into 10 raised power minus 19 joules. Right? Okay. Next is photoelectric effect. Yes, everybody. Next is going to be photoelectric effect. Now, when you talk about photoelectric effect, it's a very, very simple thing that we will talk about. It's actually very interesting also, right? This is another effect that is showing you that electromagnetic radiation has a particle nature. It does not have a wave nature, right? So we'll talk about that. So this is the last thing that we are going to discuss in this lecture, right? Because next is we are going to start with the Bohr atomic model, right? So here what happens is photoelectric effect is that just imagine that you and your friend, okay? This is you and this is your friend. This is your friend, right? You and your friend are going out. You want to go out, right? You need to ask your parents. Now, three cases are there. Your friend is actually coming to your home so that he or she can actually convince your parents, right? So one case is there that he will be able to convince your parents and you will go out. Other is that, and parents will also give you money. Second case is that you will go out, parents will be convinced, but with no money. They'll be like, you want to go out, you go out, but we will not give you any money. Have your pocket money and go out, right? Third is no going out. That the parents will be like, we don't care, we don't want you guys to hang out, just relax. Okay, so these are the three cases that is possible, right? Similar is photoelectric effect. Same as photoelectric effect. Same thing. But in this case, what happens that this particular parents is the metal, right? And metal has atoms which has electrons. So I am just writing these electrons here, right? You have your friend named Mintu who is actually convincing your parents, and you are Chintu. Okay? Electron is Chintu, Mintu is the incident light that is coming, right? So incident light is falling on the metal. When it falls on the metal, if incident light is like able to convince the metal that can I take him out, please, we need to go. We also want to have, fun in our life, right? We want to go out and just watch a movie, that's it. But the parents are like, okay, you can go, but you need to come back after 3 hours, right? We'll be like, okay. Now, parents are like, okay, this is money, you take it. Then you are going out. Similar thing happens with this one. This incident line, if it has enough energy to take out the electron, it will take out the electron with the kinetic energy, right? Electron is taking out, but with kinetic energy also. That is your money. Second is, it is incident. Everyone is like, oh my God, parents will be convinced or not. So parents are like, see, it's okay, you want to go out, you can go out, but we are not going to give you any money. You already have pocket money. If you have savings, you can go out. If you don't have savings, we can't do anything. So you're going out, but without money. In this case, incident light has enough energy to convince the parents to go out, but convince the metal so that electrons can go out, but not enough to have kinetic energy. In the third case, you are trying to convince the parents. Parents are like, we know all these tantrums that you have. Don't throw at us. We have also went through your age, and we know that what you guys are up to, right? So just relax and just sit at home. Focus on your JEE preparation. And you are like, oh my God, why my life is like that? And you are still here in your house, right? So here, electron will not be able to get out. Electron will not be ejected, right? So what I am saying here is that there will be 3 cases. One is, let me just show you that. One is that in this case, incident light is E, and that is called H mu, right? Energy of incident light, that is photon, is H mu, right? So it will change. If you have red color, mu will be different. If you have yellow color, mu will be different. According to that, it will change. Second is, this metal, whether it's sodium, it's zinc, it's cesium, it's copper, it will have different work functions. See, all the parents are not same. Some parents are very chill, some parents are very strict. So all parents are different, but it's not like parents are different, then they will fluctuate, right? They will not fluctuate in their behavior, right? They may get convinced or not. That depends on the external factor. But for one parent, the level, the work function, we say work function, that is the energy that is there for the electron ejection required, right? The energy that required for electron ejection is H mu naught. That is the work function that is denoted by W naught. And the rest is your kinetic energy, right? So if the energy of incident light, if I say that energy of incident light is very high than H mu naught, then electron will be ejected plus kinetic energy will be there. Because energy is very high. He's like, you are like my parents. You don't know, I'll take care of him like anything. I'll die, but he'll be there safe. Parents are like getting emotional. Such a best friend kind of thing is keep him safe. Why? Because you will not get these kind of best friends. Some best friends are like, they are so our parents are so impressed by them. Our parents are like, we don't know about you, but we can have guarantee for him. Right? Why? Because your best friend is so amazing. You are like bakwas. Right? So this is that kind of best friend. Another best friend is able to convince but is not able to take out money. So electron ejection is there but no kinetic energy. Then if H mu is less than H mu naught, energy required is H mu naught. Like you have to be like, hey, you are like my parents. But he's like, we were going to watch a movie. But if you let us know, then we will go. Otherwise, we can also study. Then parents will be like, then study. Then study. Will not let you go. Right? So, H mu is very less. So, no electron ejection. No electron ejection. Okay? This is the whole scenario that is happening here. Right, everybody? Now, I'll tell you some very, very important simulation here, which is going to actually show you what is going to happen here, right? So black body radiation we've already seen. This is the next simulation that we have here. Students, let me see if you're able to see this or not. I am not sure about it. So I think now it will be more visible to you guys, right? Okay, yes. Now let's see this, guys. Let's see this, okay? So this is the incident light, right? This is the electrode. This is the metal, basically. This is metal. This is metal. And the light is falling on this metal, and we'll have to see whether some electron is getting out or not, right? So I am fixing this on sodium. I am fixing that there is sodium metal here. This is the sodium metal. I am fixing it here. Now, what I want to see that if I have the frequency, see, more the frequency, more will be the energy. So I need to increase the frequency. See, if I have yellow, blue frequency, I'm increasing, no electron is getting ejected. No electron, no electron, no electron. Wait a minute. Intensity is 0. Yaar. Intensity also has to be, intensity means number of photons also should be there. I have very high, see, simple thing is this happens in reality. I have a tube light in my home. I don't switch it on, then what's the benefit if that is a very high watt? Doesn't matter. You have to turn it on, right? So intensity has to be there. Let's keep 100% intensity and let's variate this thing. Let's say you have red color. Okay, red color of light is there. Now in red color of light, nothing is happening. Now you have light change to yellow color. I don't know if you're able to see this variation, right? I think because of the brightness, you are not able to see this, but in reality, you can look at this one. In reality, this is actually falling here. For me, I can see that this is actually falling here, right? So what you will see, in red, there is no electron ejection. As you move to yellow, no electron, green, you have electron. Can you see electron ejection is there? But can you see the speed is very slow? Because if h mu is less, the incident light frequency is less, then kinetic energy, electron will be ejected, but kinetic energy will be less. If you increase it, let's say I have increased to this one. Can you see how fast is the energy? If I increase it to more frequency, it will increase to even more rate. That means when you increase the frequency, kinetic energy is changing, right? This is a very important point. When you increase the frequency, kinetic energy is fluctuating. Reason being, if your friend is able to convince you with very high energy, it is able to convince your parents, then money will be more. Na? Parents have agreed. They're like, yes, you go, work function is already done. See, when h mu is equals to h mu naught, okay, so see this thing here, that is, when I say, once you have reached this condition where h mu is equals to h mu naught, right, after that, how many times, whatever is the extra amount, that will be your kinetic energy. So as h mu is increasing, let's say a work function required is 8 and you have reached 8, right? Then no electron will be ejected with no kinetic energy. If you have, let's say 8 but you have 10, kinetic energy go. Let's say you have 15, kinetic energy will be even more. Let's say you have here 20, kinetic energy will be even more. Because here this particular, if incident light is 20, you're taking out the work function, then you are left with the kinetic energy. So as the frequency, because this thing is constant, so as this is increasing, this is increasing, right? So that's why as the incident light is increasing, the frequency is going to increase here. Sorry, as the frequency is increasing, the kinetic energy is going to increase here, right? Now, I want to change the intensity. Let's keep the intensity 7, only 1, 2 electron, 3, 4 electron, more electron, more electron, more electron. Can you see as the intensity is increasing, intensity of this light is very sharp, very bright or very dim, depends upon that. As the intensity is increasing, number of photons are increasing. That means we are saying that one photon is going to take out one electron. If one, let's say you and your brother wants to go out and there is some common friend, right? So the rule is that one friend is going to take out only one brother. You need other friend to take out other brother. Okay? So one photon is going to take out only one photoelectron, right? Because one photon is going to collide on the surfaces of the metal, and then it is going to exchange its energy. It's like this is photon, this is electron in the metal. It is going to collide here and it is going to give its energy to the electron so that electron gets ejected. This is the whole process that is happening, right? What is the whole process, guys? Understood now? What is happening here? What is happening here? This is you, this is your friend, okay? So this friend is going to collide here and transfer. This is photon, this is h mu, this is electron. So what will happen? It is going to give its energy to the electron so that this electron starts moving, right? This is transfer of energy is happening in reality in the photoelectric effect. Okay? Yes, everybody. Now, this also I told you. Now, observations, for observation, rather than telling you theoretical thing, I'll more focus on this thing only. So, first observation, we observe that as frequency increases, kinetic energy increases. Second observation is that as number of incident photons are increasing, the electron ejection is more, right? Third thing that I can observe is here, this is the fluctuation of frequency. This is the fluctuation of incident light. This whole we have seen. Can we see that when we talk about calcium, what happens here? Nothing is happening. Sodium, electron is ejecting. Zinc, nothing is happening. Copper, nothing is happening. Platinum, nothing is happening. That means, let's make the frequency more. Let's make frequency more means energy is more. Now let's talk about calcium. Yes, now calcium. See, calcium here it was not able to extract electron. Sorry, here it was not able to extract the electron. Right? If you see over here, no electron ejection is there from this side. Then as you move to this side, electron ejection is there. As you move to this side, electron ejection is more. Right? Okay. So that means the electrons you can see are moving with high energy here. Right? Can you see? High energy. Energy is changing entirely. So let's talk about this thing here. This particular. Now I am fixing the intensity to 100%. I am fixing the frequency also. If I change sodium, sodium will have more kinetic energy. It will work function depends. Zinc, no electron ejection. Copper, no electron ejection. Platinum, no electron ejection. Calcium, electron ejection is there. That means, can you see it depends on the work function as well. If work function is high, if this work function must be low. That's why less incident light is required. Less energy of incident light is required. Let's say zinc was a very stubborn person, right? So zinc, if you have here, it is not able to extract any electron with this frequency. With this frequency, no. With this frequency, no. Here it is able to extract because if you have more work function, you require more incident light. You require more energy of incident light. Let's say, ma'am, let's talk about this. Okay, ma'am, can I increase the intensity? See, zinc, at this there is no work function. Sorry, there is no electron ejection. See, I have kept the intensity to 100%. Still there is no electron ejection. So that means Intensity will not tell you whether there will be electron ejection or not. Intensity will only tell you, intensity means number of photons will only tell you whether how many electrons will be ejected. So number of photons is not telling you whether it will be ejected or not. What will tell you, if H mu is equal or greater than H mu naught, only then electron will be ejected. No matter if your H mu is less than H mu naught, no matter intensity is 100%, see, nothing will happen, right? You have to change the frequency if you want actually this to happen. Okay, everybody, clear? Clear? So now let's talk about the observations and the graphs here. Then we have some questions and that's it. So let's see this here. So first is observation number 1 is that kinetic energy is directly proportional to frequency or h mu or energy of incident light will define the kinetic energy. Okay. Then second is, if you have intensity, what is intensity, guys? Intensity is number of photons. Number of photons. That will define number of photoelectron, number of electron ejected. Okay. Third is more work function. More work function. More the H mu required. Okay. It means H mu has to be greater than H mu naught. H mu has to be greater than work function. Okay. These are the 3 observations that we can make from here. Right. Now we'll talk about this, the same thing that I talked about. Right. Now guys, what is this work function also we have talked about. Now what is threshold frequency? This mu naught is threshold frequency. Right. The frequency of the electron. Right. That means how much frequency is required to take out the electron. Minimum frequency that is required. Right. Now what is stopping potential? That is V naught. See, this is mu naught. This you have to see. This is actually mu naught. This is mu. That's why I have drawn it like this. This is mu naught, right? And this is V naught. That is stopping potential. Stopping potential is you apply outside potential to stop this particular situation, to stop the ejection of electron. The potential that you apply is called the stopping potential. The potential required to stop the removal of electron from the surface of metal is called the stopping potential. Now, if you see, kinetic energy is equals to charge into stopping potential. Here, charge of electron is E and stopping potential is, let's say they are saying that it is V naught, so I'll take it as V naught. And so this is going to be kinetic energy. Kinetic energy is also equals to half mv square, where V is the velocity, m is the mass. Okay. Now let's talk about the graphs here, guys. Let's talk about the graphs. Very simple graphs you have here. Okay. Very simple graphs you have here. Let's talk about these graphs here. Right. Okay. Sure. Let's talk about the graphs here. The graphs are effect of frequency on photoelectric effect. See, first graph is between kinetic energy and frequency, right? So as we know that energy is that kinetic energy of the electron, right? This is the frequency, this is the kinetic energy of the electron, okay? So we know that as the frequency, when the frequency is lower than, if this is mu naught, when it is lower than mu naught, nothing is going to happen. When mu is less than mu naught, nothing will happen, right? Because no electron ejection, no kinetic energy. As soon as it is equals to mu naught, electron will be ejected. But after that, if mu is increasing, kinetic energy is also going to increase. This says that kinetic energy is directly proportional to mu till after mu is greater than mu naught. Only after that kinetic energy will be greater. Otherwise, it is going to have no effect. Next is going to be electric current and light frequency. As I told you, as frequency increases, there is no effect on the current. Current means how much number of electrons are ejected. Number of ejected electrons are dependent on the intensity, not on the frequency. That's why it is going to be constant. For if you're increasing the frequency, current is going to be constant. It is not going to change, because current is number of electrons ejected, and number of electron ejected is dependent on the number of photons, not on the frequency. So that's why it's a constant graph. These graphs are very important. Okay. Then if intensity is increasing, this I told you that photon, electron ejected is directly proportional to photon. So more is the number of photons, more will be the electron ejected, more will be the current. This is nothing but current, and this photon is nothing but it is intensity. Okay. Next is, in this graph, what you have is stopping potential. Okay. So you are applying some potential from outside to stop the process. See here what will happen. We are saying frequency and stopping potential. See, tell me one thing. As the frequency is increasing, what is increasing? What is increasing? Work function is same. Remember that work function. Kinetic energy will increase. So, we know that kinetic energy is equals to E into V naught. Kinetic energy is directly proportional to V naught. And we know that kinetic energy is directly proportional to mu, is directly proportional to V naught. That means, can I say mu is directly proportional to mu naught? As the frequency is increasing of incident light, it is giving more kinetic energy after it has achieved mu is equals to mu naught. So that's why we have drawn this graph only after mu is equals to mu naught. Mu is equal to, you don't need stopping potential. If mu is not equal to mu naught or even greater than mu naught, not even greater than mu naught, then no electron is ejected. Then you require zero stopping potential. But if mu is greater than mu naught, right, kinetic energy is being released. That means to stop that, you have to have more potential. So more is the kinetic energy, more is the frequency, more will be the kinetic energy, more stopping potential will be required to stop the electron. If someone is running through a very high speed, you will require more potential to stop them, right? Okay. Now, next is these two graphs, okay? So these two graphs are very, very important. See, this can be little difficult for you. This is actually based on the experimental data, right? See, remember one thing, that if we talk about here, you have a battery, right? Potential of the battery, current will increase firstly, then it will become to a saturation point, right? And if you decrease the potential, what will happen here? It will start decreasing and becomes zero. It will start decreasing, become zero, start decreasing, become zero. This is an experimental data. Okay. If you talk about this thing, same thing will happen here. If you talk about this, we are talking about, let's say in different conditions, we are talking about this thing. And if I am saying that same thing, here, if you increase the potential, collector plate potential, it will increase the current, right? But when you decrease it, it will decrease. But when you decrease, that means when you have retarding potential, when you have negative potential, it will decrease like this. When you have retarding, it will decrease. When you increase the potential, it will increase, right? So if you're like still confused in it, then I'll just show you here. This is based on this particular experimental data. Okay? So this is the voltage that we have to change. This is the voltage that we have to change. Based on it, current will change. So this is the experimental data, right? You can yourself, try this out, and fluctuate it. You will see that it is actually happening. So it's an experimental data. Nothing to explain in this, right? Okay, everybody. So now let's discuss about the questions here. The first question is JEE Main 2022 question. Everyone focus here on the questions. Yes, students. Beta, my health is not fine today. Right? So let's do the questions because otherwise I'll faint. Right? So the energy of 1 mole of photons of radiation of wavelength 300 nanometer is how much? So now they have given you 1 mole. That means Avogadro's number of particles you have of photons. Wavelength is 300 nanometers. So we know that E is equals to NH mu. NHC by lambda. So lambda you have, number of photons are given to you, H and C is a constant, so you can directly apply this value here, right? Okay, so same thing. Acha, this formula, na, this is important. Now, what is this formula? See, this is nothing but they have just written the value of HC here, that's it, nothing else, right? So if you put this in lambda in nanometer, you will have the answer in electron volt, right? So here E is equals to 1240 by lambda. If you put this in nanometer, this will be in electron volt. You just need to remember one formula. Okay? Okay? If this is given in Armstrong, converted into nanometer. If this is given in meter, converted into nanometer. Okay? Okay? Right? Now, let's see, if this is given in Armstrong, you can put a 0 here as well, right? But I would advise that just remember one thing, in nanometer, you have 1240 and answer will be in electron volt, right? So this is for one photon. This is for 1 photon. You have Avogadro's number of 1 mole of photon. So this will be multiplied by Avogadro's number and hence you will have your answer. And if you see the question, the answer they are asking you is energy of photon radiation of wavelength this. Here they have not actually mentioned that what you will calculate here, right? So that is a demerit here that they have not mentioned it here. So in electron volt, this will be the answer. And how to convert electron volt into joules? Multiply it with this particular number. That's why I don't remember too many formulas. There is a formula that if you want to calculate this in centimeter, it is 2 into 10 raised to the power minus 25. You will get confused in that. So rather just remember this thing that if you have lambda in nanometer, in electron volt, apply this formula, right? And if they ask you in joules, multiply it with this one. In kilojoules, convert joules to kilojoules, right? Okay. Now, next question is, this is based on photoelectric effect. If P is the momentum of fastest electron ejected from the metal surface after the radiation of the light having wavelength lambda, then 1.5 P momentum of the photoelectron, the wavelength of the light should be. Okay. So, kinetic energy of the ejected photon is very high in comparison to the work function. Okay. So, that means this is the H mu. The momentum they are asking now. So see, in terms of momentum, you have to write the kinetic energy, right? Okay. So that means your formula is going to change here. We know that kinetic energy is equals to P square 2m. Now, those who don't know, it's very simple. You must have done in your class 9th also. Is half mv square. When you multiply it by mass, you divide it by mass, it will become something like this. It will be 2 mke. This mv is nothing but momentum. So you can say kinetic energy is equals to P square by 2m. That's how you have this particular formula. Okay. This you have seen in lower classes as well, right? So just put this here. Now he is saying that momentum of the fastest electron from a metal surface after the radiation of the light having wavelength lambda and momentum is 1.5. Fastest electron is having 1.5 momentum. Okay. Now, the wavelength of the light should be. Okay. So two equations we can make here. One equation is this thing when we convert it simply. But now when they are saying that the momentum is 1.5 p of the before, right? P is the momentum of the fastest electron ejected from the metal surface after the radiation of having given this. Then for this much momentum of the photoelectron, they have given that for P momentum, which is for fastest electron, the wavelength is lambda. The wavelength is lambda. Hc is constant. Work function for a metal is going to be constant. Usually in some books, work function is also denoted as phi, right? It is basically W naught also you can write. Next case is Hc is constant, but now momentum will change, so Hc will change, right? This work function is going to be constant for a metal. Now mass is also constant here. This is changing to 1.5. They are asking what is the value of this lambda 1. So these are the two equations that you have. Tell me beta if that is clear or not. You had E is equals to mu naught plus kinetic energy. Okay? Their work function is constant. Right? Here this is hc by lambda. This is equals to p square by 2m. Here momentum is changing and lambda is changing. Rest of the things are constant. When they are saying that, well, momentum is p, lambda is lambda, simple. When this is 1.5p, you have to calculate what is the value of lambda. We have taken it as lambda 1. Now, these two equations we have, we'll just add this up, and what you will have when you are adding these equations. Now, this is solved in a different form. You can solve it howsoever you want to solve it, right? So, if you neglect the work function, right, because this is actually a constant thing, you can write it like this. This is the easier way to calculate this. Then you divide both of them because work is constant, right? Work function is constant here, right? So it's like you have 5 is equals to 2 plus 3 and 7 is equals to 2 plus 5. So this work function is constant here. That's why they are neglecting this thing here, right? Okay. So let's talk about this thing. After neglecting, right, this thing, you have this particular equation, then you need to just take the ratio of it and you will have your answer. P square will get cancelled. It will be 4 by 9. So lambda 1 is equals to lambda. You want to solve it by some other method, you can solve it. Just remember, these are the two equations that you have to solve, right? P will cancel out, 2m will cancel out, work function will cancel out, hc will cancel out. And in the end, you will have relation of lambda 1 and lambda. Okay? Whatever you are math student, so I don't even need to tell you how to solve it, right? So you can easily solve these kind of equations. Next question is, given below are two statements. One is labeled as assertion, other is labeled as reasoning. Okay? So, statement you have to see. In a photoelectric effect, electrons are ejected from the metal surface. Yes. As soon as beam of frequency greater than threshold surface strikes the surface. Yes, that is true. Electron are ejected when h mu is greater than h mu naught. Yes. When the photon of any energy strikes an electron, when a photon of any energy strikes an electron, in an atom, transfer of energy from the photon to electron takes place. Yes, that is also true, right? So answer will be A is true. Acha, A is true. Wait a minute. Why R is not true? A is true, R is true. This answer will be A, okay, not C. Okay? Answer will not be C. Because transfer, when the photon of any energy strikes in the electron in an atom, transfer of energy from photon to electron take place. Yes, energy transfers here. So answer will be that both are A and R are correct, but they are not reason. They are not telling the reason behind that. They are not the correct explanation. Because if you ask about the correct explanation, why electron are ejected from the metal as soon as the beam. No, they are giving the reason here. They are giving the reason as well. right? They're giving the reason as well. So why the photon is ejected? Because energy transferred is to that level that it can get ejected, right? If the energy given to you is enough, this is photon, this is electron. If this is h mu, this is h mu naught. If energy provided to it in the collision is good enough, the transfer is good enough that the electron can be ejected, so it will eject, right? So they are giving the explanation also. So answer will be D, right? Okay. Sorry, the answer will be A. Yes, both A and this are true. R is the correct explanation. Okay, so answer will be A. Next is JEE Mains 2025 question here. That is, which of the following statements are correct if the threshold frequency of cesium is this much? Now, this is a very important question because I feel that this is based on the factual data. So you might end up doing mistakes here. So here it is. When cesium is placed inside a vacuum chamber, the M meter connected to it and the yellow light is focused on cesium, the M meter shows presence of current. So here you need to know about the facts also. Cesium's work function is enough so that yellow light can actually give out electrons and current can be produced. So with yellow light, cesium can emit electrons. Yes. With the is dim, the value of current in the emitter is reduced. They are saying if yellow light is dimmed, yes, if intensity is low, intensity is decreased, current in the emitter is reduced. Yes, the current will be reduced. This is also correct. Now, ma'am, how will I remember this? Beta, this is a factual thing, right? Cesium, this is how JEE asked the question, right? So that too with question practice only, right? When a red light, see, this is Vibgyor, okay? Red light will not have enough frequency because frequency of violet is maximum, yellow is still good. So red light will not have enough frequency to eject the electron, so the current will not be produced, right? This is a wrong statement. Blue light, see, obviously, see, you just have to remember that yellow light is producing. If yellow is producing, then green will also give, blue will also give, indigo will also give, violet will also give. So blue will also give. So this is correct, right? White light is a combination of all the lights. So it will definitely form the current because white light is a formation of all the colors Vibgyor, right? So that means answer will be A, B, D, C is the correct answer here, right? A, B, D, E is the correct answer here. Okay? What you have to remember here is just one point you had to remember here, that cesium gives, with yellow color, cesium is going to produce current. So if you talk about Vibgyor, right, this is yellow. If here it is producing, with green also it will give, blue also, indigo also, violet also. With the red it will not give, right? This is a factual question. Okay guys, right? Now this is a question for your homework, that is JEE Main 2019, not 29. The upper stethoscope consisting of the ozone layer protects us from sun radiation that falls in the wavelength of which region? Factual. Then the frequency of green light is this, its wave number is going to be what? This is the second question for your homework. Right, everybody? Yes, everyone. Let me know in the chat box if that is clear to all of you or not. Right? Is that clear, everyone? Is that clear? So, that's it for today, students. And one very important, this is our JEE channel where you can see like all the updates regarding our live classes, right? And just scan this code and you will be landed to our JEE page, right? And here, guys, I am waiting for your homework and I really want you guys to comment it down and write down your homework. That will also appreciate me as well, right? Rest is totally your choice if you want to do DPPs or not, but I have provided you the DPPs, right? Okay, so let me just show you that over here. What you will see is this is our Sigma batch 2026. So guys, click on here and this is the batch that I was talking about where all the live classes, mock test, Your test series are being taken after every 15 days. There are mock tests. And not only this, right? You will also be having like separate doubt sessions in the class, quizzes and leaderboards. Tattva modules will be provided to you. So all the things are there in this batch, that is at 4999. You can click on view courses and you will have separate plan for this one. Sigma, when you want to have Tattva JEE plus 12 books plus QR cards, that is for 9999. Okay, yes, so that is our Sigma batch. You can just click here and you can go and view the courses and purchase this, and I'll see you all in the batch, right? So we are also there in the Sigma batch and students are totally loving the batch, right? Chal. Okay then students, now I'll take your leave, bye bye, and I would love to see your homework in the comment section, right? Okay, if you have any doubt here, you can always let me know in the comment section regarding all the doubts that you have. Okay students, yes, okay then, bye bye, take care, bye bye everybody, bye bye.